So today we look into the introduction. I mean, it's just very basics introductions, brief introduction to let you know what is this topics about and its developments, some fundamentals, the steps, okay? Where when later on when we go to in a little bit in depth into a particular topics, then you will be easier for you, okay? It's clearer how it is being solved using these methods. All right. So just to share the introductions. So it is becoming a popular or more very powerful tools, okay, for these so-called numerical solutions. Of course, it is not only limited to a specific solving specific engineering problem like solid mechanics. No, it is now is very powerful. It can solve a very wide range of engineering problems. Not limited to solid mechanics. It could be fluid mechanics, heat transfer related, even up to acoustics. A lot. Okay, a lot of problem that it can nowadays it can use. Okay, to solve. Right. So applications, of course, if you are looking into that, like what I mentioned to you, solid mechanics, we are dealing with deformation, stress analysis. Yeah, so it is very fundamental analysis that where it started. So it can cover different applications if you are looking into deformation, stress, civil structures, automotive, aircraft, buildings, bridges. It can cover up to all these So of course, this solid mechanics it go to analysis of heat flux, fluid flow, magnetic flux, flow problems, computational fluid dynamic problems. All can be done nowadays. Okay, using these FEA tools. Okay. Why it is become so powerful? It is very related to the advancement of our computer technologies, and also the CAD systems, or what we call the CAD modeling tools that we are having nowadays. So all these two, you see from time to time, year to years, they keep improving. So now we could have very powerful or very high speeds or high and specification of computers nowadays, okay, and it can help us, okay, because of this advancement, then it can help us to solve a very complex problem in these finite element domains very fast, in a very quick or very fast way. So that is because of this. At the same time, the CAD modeling tools that we are having, like for example, one of it that you are familiar is the SolidWorks. Okay? So it keep improving. I mean, every year they come with new versions. Then yeah, a lot of improvements every versions. Then that the whole idea is to help the users to model a very complex models or complex system in fastest or in a very easiest ways. So because of this advancement, then it helps a lot in using this so-called advancement or making use of this advancement to help to put everything in the finite element domains, okay? Then to solve this problem, this complex problem, okay, in these domains or what we call finite element domains, right? So why we need that, especially the design in the design stage. Okay, this finite element analysis is a very powerful tools. I would say that as for our engine, as an engineers, right? I mean, when we come up with design or an analysis, we always need data. Okay, we always need results. Okay, to what we call here to present, to convince whoever, I mean your client, your superiors to, yeah, my design is good, my analysis is accurate, my analysis is correct. So this this is a platform or the tools that where we use to do all these things. I mean to come out with a so-called objective results, or what we call more convincing analysis data, okay, engineering data that can be used to prove our designs. So we don't just say it, okay, verbally, yeah, my design is good based on its physical appearances, because the CAD software now can do a very fancy designs. Yeah, my design is good. But then in terms of its safeties, in terms of its practicality, is it really good? Then we need analysis. So this analysis that involve basically usually is our using finite element analysis to help us to analyze our designs, to make sure our design is good, safe, practical before we really come out with the first prototypes. So yeah, we can play around with different analysis, different design, different dimension, and optimize it before we really build that things out physically. So virtually it can be done many times. So that is the beauty of what we call using these tools. Okay, the first thing is to help us to help us come up with a more convincing engineering data. So as an engineer, we use this data to prove, okay, to convince people. All right. At the same time, it helps us to come up with a more optimum designs, okay, before we build it, our design, fabricate our design physically, right? So it will be very cost saving in this case, and also probably time saving, okay, in this case. So so you see, I mean, the advancement of computer technology, the CAD software, as well as this FEA tool itself, every year it is improving. I mean, it come out with every very new version or very new features. So if we keep pace with this development, probably we will probably understand better, okay, and we can make use of this tool to help us in our daily so-called engineering design works. So you see the theory, we need to basically know, okay, the basic theories, how it is being formulated, how it is being solved, right? That is very important. Of course, modeling technique is also very important in if you are using this type of tools, then you need to model it correctly. So before you can actually send the model to the solver to solve it using these finite element methods. So I would say that if we understand the theories, the modeling technique, and its what we call the computations parts of this these FEA tools, probably we can master it at a different levels. Okay, so that is what it means by this, right? So the whole idea, I mean, of these methods of analysis is basically it finite elements. So basically, it discretize your whatever models, your whatever system under analysis into what we call elements. Okay, a simple geometric shapes called finite elements. So a continuums of models, then it being discretized into elements. Okay, and it's you have a numbers of elements. So when you have these elements, then probably you need to also understand a little bit on its governing relationship or governing equations that you are going to solve. So the formulation is also important. So later on, we'll see how we formulate the problems, okay, when we are dealing with different topics like beams, axial member, how we formulate it so that it can be solved using these finite element methods. So once it is being discretized, it is being applied, what we call building the formulations, assigning the materials, okay, of the properties of the element itself. Then a lot of time it also have to consider the loadings, the boundaries, the constraint that go into that each elements. Then you combine them to become a set of equations. Then you solve it either manually or going through a solver to solve it. Okay, solve the problems using the solvers in the FEA tools. So to highlight again that this is the FEA or FEM itself is a approximations of, or what we call a numerical solutions. So when we talk about numerical solutions, always is an approximations of your problems. Right? The problem to be solved is actually approximated. So how good or how accurate is your approximation is depends on how accurate or how good we understand the problems, we formulate the problem, and like for example, you discretize the models, you assign the properties, material properties, right? And you formulate it, how you formulate, and also how you consider the loading, the constraints. All this basically is the will affect our approximations. So to take notes on this, okay, the solutions is an approximations from FEA is an approximation, and a lot of time it affected by or a lot of factors here. It could be the how well you discretize it, what the material, what the correct is it your correct material is using, the how you formulate it, okay, the governing equations, how you consider the loading functions and also the constraints towards the model that you are by analyzing. Okay, so later on we'll look into this in more details. So if you look into classical, we try to differentiate them. A classical method, of course, is the analytical methods, and it's giving us the exact solutions. So what you do is basically you solve that what we call differential equations, okay, the governing equations. Then to get to solve whatever you have solved it, the differential equation, then you get what we call its exact value or exact results data. So when we talk about numerical methods, right? So there are few types So finite element is one of it. Okay, so boundary element is basically a model you are considering or you are discretizing the to elements on its boundary itself. Okay, then we have finite difference methods, right, and finite element methods. So that our focus is on finite element method. All of these numerical methods are only approximates. Okay, it depends on how. Basically, the whole idea is approximation in solving the governing differential equations. So again, you have to formulate the equation, the governing equations. How you want to formulate it, you have different methods. So solving using the either finite difference, finite element, or boundary element methods. Okay, the historical background of basically this FEA or FEM it started with aircraft structural analysis. So back to 1941. So we have the first so-called this. They are using research or the work reported using this finite element method in solving again solid mechanic problems, okay, elasticity problem, particularly on frames, structural frames. Then we have also you see, I mean, from time to time we have looking into using these methods to solving different type of applications, trusses, beam, other elements. So from time to time it start improving, And the words finite element only started to use in 1960. Then from there, right, so we look into approximation solutions in problem not only limited to stress analysis or solid mechanics, it could be fluid flow, heat transfer, and other areas. And 70s, 1970s, early 1970s, in fact, these particular methods or analysis is already applied up to non-linear problems due to large deformations. So here, of course, we are still dealing with linear problems. Okay, so don't go up to non-linear. So particularly on solid mechanics. Area applications here, if you look into this, like I mentioned to you, it could be very broad, right? So of course, our focus is on structurals, solid mechanics, static, stress analysis, dynamics there. So heat transfer, fluid flow computation, the fluid mechanics, even electromagnetics. I think the reason one is quite very powerful is the acoustics. So a lot of, we use these acoustics to solve some. We use these FEA tools to solve some acoustic issues or problems. For examples, that I recently read or attended a conference. They're using this for the what we call the trains, our MRTs, our LRTs. Okay, the noise created by these particular trains. Okay, so they analyze it using the acoustics tools that available in these FEA tools lah. So particularly into analyzing how the sound, the what we call the sound, what we call pressures or the noise mappings. Okay, from there they come out with noise control methods using these particular tools. So it's quite powerful. Advantage. Okay, so of course you compare to finite difference or boundary, right? Boundary elements. Boundary element, of course, is looking into boundary, not into the entire shapes of the models, right? Finite element, it consider the entire shapes. Compared to finite difference, then it is finite element is better in dealing with irregular boundaries compared to finite difference. So body with irregular boundaries, yeah, it's very good when we are dealing with finite elements, when we're using finite element methods. Then you have general loading conditions. Okay, different types of loadings can be applied. Okay, in this, if you are using these finite element methods. Different material properties, so you can have this particular part is this material A, this particular component is material B, can be done, can be applied differently. Various boundary conditions, you have fixed, you have free, you have different type of boundary or constraints. Okay? At the same time, it allows to use different, what we call the size, the discretizations of your elements. It could be different types. There are a lot of element types, element size that available that can be used. That all of these will basically relate heavily to the accuracy of the approximation that we will be having, okay, in our solutions. And of course, if you're using these methods, then it is easy because that is how you formulate it in the more in towards matrix forms, and you can easily modify your so-called your matrix matrices, then the size of it, then you can always reanalyze it. So it is quite convenience, okay, when you are dealing with this. And not limited to statics, of course, it can go towards dynamics analysis, non-linear, okay, in terms of the geometry, in terms of the materials used, so also can be used to analyze. Software, when we talk about software, we have a so-called two types here. Finite element software, we have two types, the tool cell. So this computer software and also the advancement of the hardware computers basically make it popular that I mentioned to you. So here we have two types, small and special purpose programs or software. So this small and special program basically is it aims to solve a certain component or certain parts of your models So if particularly let's say beams, then it will only use to solve a problem that related to beams using these finite element methods. So let's say you have trusses or frames, then basically it use this particular program to solve only trusses or frames. So it cannot solve other things. So is very special. So that is very small in size and is very specific to certain problems, solving certain problems. Okay, so fluid flow, then basically all the program is mainly on formulation of how you solve that the fluid flow problem using the sim formulations, then using so-called different element, different types of whatever. So that is a specific purpose or special purpose programs. Of course, we have from here we also have large general purpose program. That is where we usually see the commercial program. So specific or small special purpose or small program, usually maybe you can get it for free from anywhere, but it's not maybe it's a coding types. It's can be run in MATLAB types. It's more toward what we call a small or small size or small scales of programs where you can use it to solve a specific problem using FEM. So this large usually is the commercial one, a large general purpose. It could be general purpose, then usually is the commercial program like what we have in NCIS. Okay. So if you are talking about the advantages of this commercial software, so these are some of the advantages. Compared to the small program, small types of program or special program, of course, it involves a lot of the formulation, how it's being formulated, how it's being solved, involve a lot of codings, computation. So commercial software, of course, it won't let you see all these codings or these so-called solutions types. It's black box. So but it kind of designed in a very user interface, user-friendly interface. So-called you can use it easily in terms of insert the parameter, input your parameters to be solved or models, everything. So it is kind of a very easy input for pre-processing. I mean pre-processing meaning before you start solve it, you have to do all this kind of insert things before you start the solution. So it make the whole thing easier. I mean, how you import a model, how you set the material properties, how you set the loading, how you set the constraint. All these things can be easily done in a commercial software compared to the small type. Small type, you have to find where is the coding, where you have to put the stiffness, materials. It won't give you just materials. You have to ask. You have to find the materials. Still, then you have to find the stiffness of the Young's modulus yourself. You have to insert it. So in this particular software type or commercial software type, you do not need to go and manually find it. Basically, use. Let's say it's a structural steel. You select structural steel. It will have all this data available for you. The material properties for us. And convenient outputs, so it can be post-processed to what we want. If I want to see stresses, then it will show it will compute the stress and let us know. In terms of the values, in terms of what we call graphicals, I mean the stress contours. deformation, strain, everything can be called out and displayed or computed easily, or when it is being solved. So it's very convenient. Compared to maybe small size one, it's solved, you formulate it, okay, then you solve. Later on, you'll see it will in our manual theories, but you will solve, let's say, deformation. So if you want probably the value, you want the full contour, probably you need another type of software to help you to plot the entire so-called deformations contour, something like that, or stress contour. That's so not that convenient in that case. Solve many type of problem that I mentioned to you, in not limited to solid mechanics. It can be fluid flow, heat transfers, acoustic, even they can be combined, okay? Like couple together, fluids with structures, heat transfer with structures, then acoustic with structures, heat transfer with fluids. So all can be coupled and solve a very, very complex problems. So it can solve many type of problems. And it is modular, okay, usually. So because it's general purpose, you have many features or solvers, okay, covering different type of tests or application. So it's modular. So if I just want to look into structurals, okay, then I will just call the structural module coming out to solve it. So if I want this fluid flow, then I will just call that module coming out to solve the flow. So like I want to couple them, combine these two analyses, then I can call these two out and link them together. So I have the result of structurals, okay, is taking into consideration into the fluids, and the effect of the fluids flow will take into consideration into our structural deformation, something like that. So it can be, because it's modular, then it can be basically what we call out, okay, and link together easily. Of course, desktop computer lah, it have to be installed in the desktop computer, and ownership cost is low because we don't own it, we don't need to maintain it, okay. Yeah, we don't need to really from time to time, and let's say you have anything that need you to maintain, or there is a bugs or whatever, then yeah, you don't need to go through all this lah. Will be taken care by all this the manufacturer, or what we call the commercial software provider lah. Okay. Of course, you have advantages. You have also the disadvantages of this software lah. So it is very high development cost lah, because you are covering so many types of applications, so many types of analysis. Then the development cost is, of course, is very, very high. That's why it required licensing or arrangement. So usually small types it can share with for free. A lot of time you can find this small special purpose type of program, okay, online for free, that a lot of researchers willing to share, because it just solve a specific type of problems. But dealing with this commercial software where it's general purpose, it can solve different type of analysis, then because of the costing, development cost is high, then yeah, it requires licensing. So for example, we have our so-called teaching one, the license, like our computer lab, we have the teaching license. I mean, a lot of time, for example, this particular course, you are using this type of license. Then if you are doing research, okay, research based, you are in coursework, right? Master by coursework, master by research, probably if your research involving this computational analysis, then there is another type of license, which is research license, where you have more features. A lot of time is the element types or elements size that available, okay. I mean, there is a difference between this type of licensing. When we said less efficient than smaller program, of course, yeah, because when you talk about this small program or special purpose program, yeah, it designed just to solve that particular like beams problems, okay. So it could be more efficient in terms of solution or in terms of solving it, right? So very straightforward, you can solve it, then you get the data. But like for example, you want to display it in terms of its output result, then it's not that convenient using this small program. But in terms of solution, it's more efficient compared to the commercial types. And yeah, you using this commercial software usually is as I mentioned, is black box. You do not know, you have no access of the codes, okay, behind how it's being formulated, how it's being solved. But small programs, small types of program types are basically you can usually is coding types that you can access all these formulations, how it's being solved manually, right? So that is disadvantages. So because of this, we want you all to at least understand, right, the theories, the fundamental behind how the problem being formulated, and so that you can at least when you use this commercial software, you know, where to find, because you know the fundamental, the theory behind, then you know when you get the so-called results, right, from this commercial software, at least you will know whether this result is correct, accurate or not, because you have gone through this theory, you have gone through its limitation, so probably you will understand better whether the results coming out from the commercial software that you have use, okay, will be accurate enough or not. Okay, so that is the purpose of why we are going through these fundamentals. So this is a basic step in the finite element methods. So I group them into 3 phases: pre-processing phase, solution phase, and post-processing phase. So pre-processing phase here, we have first, okay, we need to have the model and under analysis. We need to know what we are analyzing. Okay, so this model is a continuum that we discretize them. Okay, we discretize it into finite elements. Okay, so basically when we dealing with finite elements, so the model basically will be divided into elements. Each element will have what we call here nodes. Right? The nodes build the elements. Then we have the next step. This is the basic steps of what later on we will make use of these steps, okay, to solve our finite element problems. Our problem using finite element methods. Okay, so next, once we have discretized it, then we have to assume a governing equation or a functions, okay, that can represent that particular elements. Okay, if you want to, for example, we want to determine the deformations. Okay, so probably we need to find build a relationship like f equals to kx to find the deformation later on, right? So that governing so-called equation, we have to formulate it up, okay? So these formulations that later on can represent that particular so-called elements as well as the entire models. So once we have that so-called governing so-called equations of the function itself, then we have to develop that equations, okay, in terms of so-called matrix formula that can represent for the elements. So that equation itself, it is representing that particular element, okay. Let's say, for example, to solve for the deformations. So once we have that, we have to assemble them, right? To from maybe what in terms of its matrix forms, it depends on how big is our model, how many elements we have, then we build it, okay, we construct it, okay, in terms of matrix form, right? So basically, in this construction of this matrix form is basically we are assembling, okay, assembling many elements into a very global so-called that represent the entire models. Okay, we discretize it, we formulate them, then we assemble it them back, right? Then we can apply constraints, loadings, boundary condition to it before we send to the solver to solve so-called what we call matrix, the equations are in the matrix forms. So that's why later on we will review back the matrix algebra and how we solve equations in the matrix forms. Okay, so from the representation of elements, okay, so basically is some sort of degree of freedoms are these elements. So you go in towards formulate them, right? Then you construct them in terms of elements forms, matrix forms, okay, for the entire models or in terms of element. All these elements is matrix form. Then you apply all these loading constraints, then you can send to the solver. Okay, so this solver basically is just solving the equation in matrix forms. Okay, so you will find, depends what we are looking into. If we are looking into a deformation or displacement, then we will find the displacement of each nodes of the elements. Okay, so we just now we mentioned that the nodes, the nodes basically build the entire element. So every single node will have values. So this value will representing the so-called, if you're looking to a displacement, the displacement of that particular element itself. So once we have this, we can of course look into other informations like as long as we can formulate or build the relationship from, let's say, displacement to stress, okay, then we can find the stresses, okay, in terms of average stress, principal stress, all can be calculated after it is being solved, right? So this is basic step. So in terms of yeah, it's the same things, okay, just to show you a little bit, okay. So first you have the models, then you discretize them into elements. Each element you have the nodes, okay, all these nodes. So from there, looking into one element, you build a functions or formulating a equation or function that can represent that behavior. So if you are looking into vibrations or dynamics, so-called dynamics of this particular model itself, then this is the governing so-called equations in the matrix forms. So from one element, assemble them, okay, to the entire models elements. So that is in the matrix forms. So from discretizations, okay, then later on you assemble them into elements, okay. This node and this node and this node will share the same information. So basically you build in terms of its matrix coming out. So you are solving this matrix, and you get the so-called the information of the natural frequencies. So once you get the natural frequency, then I can find information like response, okay, other informations from response, its mode shapes later on in that particular problems. Sorry, what's wrong? So that is how conventionally, okay, or what we call manually, we solve using, I mean, the step that we use to solve, okay, the problems. But in a lot of time in software, commercial software, it's not in this particular flow, okay, because it have to be more user friendly. So in terms of user interface, usually you model the CAD model coming out, then you export into that software, then you assign the materials that you want, okay, apply the boundary, the loading, the constraints, everything, then you define the types of analysis that you want, okay, then it will basically send to the FEA solver. So you do not know how which let's say formulation is used, which elements, how the elements being distributed, then how it is being solved, like, I mean, the pre-processor, this part, you do not know this shape functions, you do not know the matrix equation, you do not know how they assemble the element to represent the entire problem. So these three basically usually is hidden in user interface, okay, in the commercial software. So basically you send it, you say I want vibration or I want model analysis, then it will send to the whatever that you have set the model, okay, with the loading, with the material, with the boundary. send to the solver to solve it and give you the post-process results that we want. Okay, so that is how the user interface goes. Okay, usually the commercial software goes. So that part is the hidden parts, okay, in most commercial software. Okay, so once you have let's say once you have sent to the solver, solve it, so you will get the data or the software. I will show you the what we call it's results lah, post-process result lah. It doesn't come out. Sorry. Yeah, so that is will come with the result that we want. Okay, so usually that is how the user interface goes. So as I mentioned to you, it is approximation, right? This method is an approximation. So so things that or factors that can contribute or parameter that can contribute to the error of these approximations are as below lah. So the model that we are using, okay. So the physical dimension, its property have to be accurately inserted or accurately modeled. So, okay. So if your model is 1 meter, you put 10 meter, then definitely the results will be different when it going through this finite element analysis. Okay, so that will give you an inaccurate result or wrong result that the result that we do not want. So wrong input data is very important that you have to take notes. Okay. Then the fourth one, looking into this, the boundary, the constraint, the loads also important. So if how to basically apply the load that similar to the actual condition is so important. How you want to so-called constrain your models, okay, that is similar to the actual conditions, also very important. So if you apply it wrongly, then probably it will lead you to the wrong so-called results also. Okay, so that is also important. The boundary, the loading, the input data, which is the physical properties, material properties, the dimension, the shapes are all very heavily related to the results of that you will obtain in this analysis or these methods. Of course, next will be the how you discretize your models into elements. Okay, there are many types of elements. There are many types of so-called shapes of elements, so where we can use. So if you are using a not so accurate or different type of shapes and size of the elements or the types of elements, then it will also lead to a different result. So a lot of time, because it's approximations again, so depends on how small or how fine is your element you want to your model you want to discretize into. Okay, so smaller elements, discretization into a smaller element, of course, it will lead you to a better approximations or closer approximation, but again, it will lead to a higher computation cost. So you have to basically compromise a little bit. Later on, we'll see how to do these things, okay? To at the same time, you get a fair approximation. At the same time, is also in terms of the cost, computation cost is also fair. So to know, to basically in summaries, so basically to know where will induce errors in this approximation is like all the found all the data that you inserted is very important, or that the shapes, the physical property, the material property, the dimensions, the loading, the constraint, the boundary, and even the element size and types that you are using all will lead to. Okay, it's a fact. There are factors of contributing to errors in the approximations. So we have to aware of it. Then we have to take notes. So, like I mentioned to you, formulation. I think formulate your problems. Okay, is very important. So in solving in solving this especially your our our so-called finite element problems. Okay, so we will look. Sorry. So we will look into this, okay, how usually it can be formulated, the problems. So one is, of course, direct formulations, okay. Then we have using energy methods to formulate the problems. So for example, it's particularly relevant to solid mechanics related problems. So either you use direct formulations or you can use a so-called energy method. Here we are taking the finding the minimum total potential energy. So where it relate the strain energy and also the potential energies, okay, and finding the minimum total potential energy. Later on, we will try to use these formulations to solve problem of some of our solid mechanic problems. Right. Of course, there are also formulations like not that direct. Okay, I mean the problem that cannot be solved using a direct formulations or energy problem, which is more related to solid mechanics. So, for example, like heat transfer, fluid mechanics. So usually, they use these weight residue formulations. So under weight residue formulation, it basically you have to assume and basically approximates, okay, solving this particular differential equation. You have induce some error. So basically you are minimizing the errors. So you can use collocation methods, subdomain methods, Galerkin methods. So these are these are some of the popular methods that can be used under these weight residual formulations. Right. So if you look into examples, like for example, like this, so how we will see how we formulate this type of problem using the basic step that we have discussed, okay, from the pre-processing phase, solution phase, and also what we call post-processing phase. Okay, so if you have a bar, okay, you have a variable cross sections, okay, you have supporting a load P at here. Right, so undergoing a load P so it's basically axial subject to an axial loadings. So we neglect the weight of the bars itself from the analysis. Okay, uh, assuming that the applied load is considerably larger than the weight of the bar, so we neglect it. So we are interested in approximating how much the bar will be deflects at various points. Okay, so we will want to know not only at when it's subjected to this is a fixed point, this is a free point, then it's subjected to axial loading load P. Okay, so then we want to know, okay, at different so-called L, okay, at here, or anywhere of this particular beam, what is its so-called deflections, okay, in terms of Y here. Okay, so we want to know it. So if you are using direct formulation problems, direct formulation methods, first, if you look into how we solve the basic step of the FEM, we have discussed just now. The first one, under pre-processing phase, we have discretized the solution into finite elements. So first, we have to discretize it. So here, I discretize it into this example is divided into 1, 2, 3, 4 elements. So each element we have 2 nodes. So total of 4 elements and 1, 2, 3, 4, 5 nodes. Okay. So later on, when you discretize into 4 elements, 5 nodes, then later on, whenever you solve, once you have solved whatever, you will know, okay, you will only know the displacement or deflection of this particular bar itself at the node itself, okay, at node 1, node 2, node 3, node 4, node 5. So if I want the deflections at in between here, then I probably need to increase more elements, or what we call nodes. Okay, I need to have a node at here, node at here, node at here, node at here to compute the deflection. Or that is another way is the functions later on that we will discuss that we can approximate. Okay, again from these two nodes we can approximate the deflection at here, anywhere at between here or here that we don't have nodes. Okay, in that particular element. Okay, so that is how the discretization works. Okay, so here you have in a more simplified forms. Okay, free body diagram form. So you have this element itself can be represented into U. Okay, this deflection at the particular nodes, and each of these member can be represented by a spring stiffness, which is depends on the model, or what we call the element. Each element will have represented by one element. This element itself is represented by a so-called a spring, okay, stiffness, giving us a specific stiffness. Then we have to assume a solution that approximates the behavior of an element. So first we look at the one element. So looking into one element, how we want to formulate it. Okay, of course the direct formulations in this case. So here the easiest way is F equals to so-called Kx. Okay, so when you have subtracted to an F, then probably it is equal to K, and AE over L is your so-called K equivalence, okay, stiffness, then delta L is basically is your deformations, okay. So we develop the equation for an element itself, right? So we can come up with for two nodes, we can come up with these two equations: Fi KEQ UI minus UI plus 1, or Fi I plus 1 equals to KEQ UI plus 1 minus UI. So when we table this into a matrix form, then it will give us this so-called equation in matrix form that representing one element. Okay, then we have one element using this. So if we assemble later on with because we have 4 elements, total of all elements, 5 nodes. So at the end we will build a so-called a stiffness matrix that giving us a stiffness matrix, giving us covering all 5 elements. So we will later on build when we assemble this element together. Okay, so this particular stiffness or KEQ now is in terms of global G that actually representing the entire problem, and 4 elements, 5 nodes, then you have a 5 times 5 matrix. Okay, 5 times 5 matrix. So this is the so-called the first element. This is the first element. Sorry, let me draw it up. Maybe I group it so you can see. Just now we have this is what we have for first element. Then this is again is what we have for second element. This is what we have for third element. That similar with what you have seen at here. Okay, so KEQ, negative KEQ, negative KEQ, KEQ. So this particular, when you assemble that representing one element, okay, when you assemble them, then it will become something like this. Okay. We will go a little bit detail. This is just how to show you how it is being solved in following the step. Basically, this particular topic, introduction topic, is to go into more detail on the basic steps. That's it. Not really tackling the problems. So let you see how it is being solved. That's it. So you still remember when we assemble them, then we have to apply boundaries. So you have just now K, right? Then you have the K, you have the U, okay, equals to F, right? So rearrange them in the global, what we call the entire problem form. Then by applying the what we call the boundary, okay, the load, we know that the load applying at U5, right? The fifth nodes, okay, if you look into this, the load is applied at the fifth node, then we know that this node 1 is fixed, okay, have no deformations. So these are the information that we are applying, okay, the load and the boundary or the constraints. So to build the entire so-called matrix, okay, to represent the entire problems, then further by applying the load itself, you see this one previously is this thing, the stiffness, if you look into this, you have a K1 negative K1, right? So it can be further reduced to 1, 0 in this case, because our U1 we know that is 0, right? So that is things that we can further replace. Then at the same time, we have the load applied at P, right? So if we have built this global so-called matrix, right, that represent the entire problem, then this can be used to solve we solve this, right? We can solve this matrix to find our U1 until U5, okay? This K1, K2, K3, K4, K5 are all related to our A, E, O, L. So if you have the materials, you have the dimensions, then we can actually find the E, the K, right? We find the K, then we can, with the load applied, P, okay? Let's say we have the P, which is the loads, okay? You know that, okay? It's a load applied. Then we can determine the unknown, which is U1 to U5. Okay, so that is how it is being solved. When it's solved, we send to the solver. So basically, the solver will solve, okay, the equations are simultaneously. Okay, so this one you will see that it will have 4 times 4 4 equations. That basically this thing U1 equal to 0, it can be reduced to from 5 to 5 matrix now become 4 to 4 4 times 4 matrix. So here we are dealing with this particular solution. So actually it's K1 plus K2 U2 minus U3 equal to 0, our first equations. Negative K2 U1 U2 K2 plus K3 U3 negative K3 U3 equal to 0, the second equation. So here it will give us 4 equations, right? So this algebraic equations, 4 equations, we have to solve it simultaneously to get our U1 until U1 we know that is 0, then we know we need to find U2, U3, U4, and U5. Okay, so in this case, U1 is known, U1 equal to 0, so we are finding U2 to U4. What is the value? By solving the 4 equations simultaneously. So that is how it's being formulated and being solved. All right. So inserted the values only later on. So you will have, you see that you will have solving, if you have, element 1, 2, 3, 4, then you have a node 1, 2, 2, 3, 3, 4, 4, 5. So you can find the average area. Just now we have mentioned to you average area, how to find AI plus 1 divided by 2. Then you have the length, you have the material properties, you have the so-called stiffness coefficients, okay, can be found from so-called these formulas. Okay, from there you can insert into the matrix. So this is how you build the matrix, and you have the loads. Then you can actually find, you can actually find the matrix that I mentioned to you. So solving for this 4 times 4 matrix, okay, you have K, you have the K U, okay, equals to F. Okay, so that is a 4 times 4 matrix. This is a 4 times 1 matrix. Then you give 4 times 1 matrix, right? So you will solve it. You will get your unknown. So to get your U, right? So probably you have to find, you see how to solve it lah. Basically to show you lah, matrix solve matrix. You can use matrix form, okay? Later on we'll look into the solution part lah, how to solve it when we're talking about matrix. So you will have in advance, maybe I will just show you. So you have K inverse K U, which is unknown, equals to K inverse F, right? So your U that you want to solve here is U2, U3, U4, U5, right? Equals to your so-called K inverse F, which is 0, 0, 0, 0, 10 power 3, which is your P. Okay, so if you have built your K, you can find your inverse, then you can solve it. You solve your U2, U3, U4, and U5. Okay, so at the end, you find your U1. We already know that it's 0 because it's fixed. Then U2, U3, U4, and U5. You can determine by solving these algebraic equations simultaneously in matrix form. So of course, if you want, that is solution, right? Number 6 is solutions. Then we can also post-process phase. You want to determine other informations, like I want to determine average normal stress. So you know that average normal stress equal to your force over areas. Okay, so the force at that particular so-called uh, uh, what we call the elements. Then you can find F equals to this. That's now that we have mentioned, right? Then you can actually find by building this equation, then you can find your Young modulus, your deformations divided by the L itself of that particular element itself. Actually, you find the stress, the average normal stress. Okay, or as you know that our stress, okay, our stress equals to E multiplied with our strain. So your strain is the delta L over L. This delta L is your deformation between the two node itself. Okay, so again, from there you can obtain. Once you have solved it, okay, here is deformation. You can obtain other information like stresses. Okay, so that is how it's being so-called direct formulations. So using direct formulation method to solve this. So by assuming F equal to Kx or this formula, then you can solve it. Right, the minimum potential total potential energy formulation, basically you are finding what we call the external what we call the deformations. When you apply the loads, you are having these deformations. So the work done by this external load basically is stored in the form of elastic energy. We call it strain energies. So here making use of what we call the strain energies, okay, which is represented by this, okay, lambda, okay. Then you see from the force applied, then it will convert to elastic energy. Then we find the strain energy. Then the total potential energy is the difference between the strain energy and work done by the external force. Okay, so this pi itself is represented by total potential energy. So it's represented by your strain energy minus your force, so-called work done by the external forces. Again, so you want to minimize it. Okay, you want to minimize the total potential energy. Basically, is del pi del your so-called your U, okay, your deformations, okay, equal to so-called 0. Then minimum total potential energy is represented by this formula, right? And we'll go a bit detail. So the strain energy of any element, of course, is represented by this. Okay, then minimize the strain energies. I just want to show you is actually it will lead you to the same results. If this is the strain energy that we have, we have formulated, okay, using the energy methods. This is the strain energy. Then here if you are looking into here, this is strain energy in terms of elements, then in terms of nodes or elements, then minimize it, then we del lambda del u, then you have the minimum strain energy with respect to the each node. So if you rearrange this minimum strain energy in the matrix form, then you will give you something similar like what you have seen in just now in the direct formulations. Okay, so in matrix form. So if you are minimizing the work done by external force, again, Fu, just now the work done here is F multiplied with the deformations. Then the work done by the external force, you minimize it again, right? So you have del Fu del U equals to Fi. So at different nodes, you have Fi plus 1. So again, you're looking into these two when this strain energy, minimum strain energy minus the minimum work done by the external force is the minimum total potential energy. So it gives us this matrix forms. Okay, this minus this will be something similar. If you equal to 0, right? So this let me write it. Sorry. So we have your minimum strain energies, which is del A, del del U. Okay. Okay. Is your minimum minus your minimum work done by the external forces. We have del F I U F U lah. I mean F U talking about 1. Okay, in generals, F U del U, okay, equal to 0. So that is what we have del pi del U. Okay, so that is our, here is our minimum. If I do like this, that is our del pi del U. Okay. So equal to this is our minimum mean total potential energy. All right, so if you rearrange the whole thing, then it will give us the similar so-called matrix forms, okay, as we have obtained using direct formulations. So it can be done either, it can be formulated using direct formulation method or using the minimum total potential energy methods. Okay, so if you can build that the global so-called the matrix, global matrix forms for to represent the entire problem, then the solution part is the same. So that is to tell you how it can be formulated. Of course, if you are, this is again, this is a numerical so-called methods, right? Either your direct formulation using and also minimum total potential energy methods are all using finite element method. These are approximation, these are numerical methods. And you compare to exact solution, and this problem also can be solved with exact solutions, okay? So if this is how it being solved. So if in terms of static equilibriums, you have the P, the force minus the stress multiplied with the area itself. Okay, AY itself is equal to 0. Then you rearrange it, you will come out with so-called the equations. Del U equals to P del Y EAY. So basically, this is your so-called your deformation in terms of as a function of y in a function of y. Okay, so the exact solution is then obtained. You have to solve this so-called differential equations. Okay, del u, you want to find u. Okay, del u du equals to so-called p dy eay. Okay, then from 0 to u, 0 to l, then you integrate it, you get the so-called final equations. Okay, which is, sorry, which is this one, right? Which is this one. So called your U, okay, at different Y, okay, U in Y directions, okay, at different L, okay, at different L. So you can substitute your L, okay, your load, whatever your thickness, your dimensions, like everything's in, okay, and to find your U, okay, your U, your also deformations, okay, at different locations, okay, let's say at here, at here, at here. So your Y is, let's say your L is, let's say 1 meter, so maybe at 0.5 meter. Well, when Y equal to 0.5 and Y equal to 0.75, you just substitute all this information in, you'll give you the exact value or exact deformations at that particular. That is how you solve using exact solutions. So you have to build that the differential equation, then you have to solve the differential equations, right? So without no approximation. So if you look at this comparison with the exact solution result with the direct method and energy methods. So of course, direct method and energy method will be the same result because they end up with the same matrix forms, okay, the global matrix form, and the solution, you are using the same solution methods, simultaneously solve it, you'll get the same result for your each nodes or U1 until U5. So it's the same. So at the end, you found that direct and energy method are same, but when you compare back to your exact solutions, of course, there will be a slight difference. Okay? So of course, this is the most accurate one compare, because it's exact solution, but you have to formulate and solve the differential equations that is not an approximation types. And if you can see that there is a slight difference at Y equal to 2.5 is only 0.001027, and compared to 0.001026 right? And going towards the ends, free end, probably the error or the difference will be slightly larger, 0.00533 and 0.005317. Okay, so that is to let you aware that this again is numerical and is approximation. All right. So weight residue formulation also can be used to solve the similar problems. So what weight residue formulation is, assuming an approximate solution for the governing differential equation. So just now we have built the governing differential equations already, right? You build the governing differential equation, then you have to assume approximation. So basically, you are assuming this solution can be solved, but with satisfying some of the conditions, either initial or boundary conditions, and it will lead to the solution of this will lead to some errors or some residues. Okay, so that is what weight residue formulation goes. So the same governing differential equation is used, but then it is approximate that, okay, by solving using the initial and boundary condition that's set, it will lead to some error, and you would want to minimize these errors so that it's close as to the exact solution. Okay, so that is how it works. So this is the differential equation that we have built just now from the exact solutions. Okay, so it's not solved in terms of this way the exact solution ways. Okay, it's solved using the approximation way. Okay, so you see that this is the so-called the differential equation that we have built. So what weight residue formulation do is, okay, so they are doing this, okay, minus p equal to 0. We know that, okay, we arrange it is equal to 0, but subjected to u0 equal to 0. So what they do is they have to come out with so-called assume, okay, this u now is a functions, okay, a certain functions, okay, and by applying this function into this so-called differential equations, okay, and with a certain boundary and initial condition to be satisfied, then it will lead to a residue or error. Okay, so of course we want to reduce this error as small as possible, so that this solution, when it's solved, is very close to the exact solutions. Okay, so if we do not know u in terms of y, a function of y is what? Okay, so we approximate this. A function is a function of cubic. Okay, then we substitute into the differential equations. Okay, then we assume that there is an error, and we are minimizing these errors. Okay, so collocation method is assuming that the error or the residue, okay, the function r, just now we assuming this is our so-called the error, okay, that will induce an error, r, okay, is r. So this r is forced to be 0, okay, we have to force it to 0, so that as many points as possible at different so-called boundary, okay. So when y equal to L per 3, we want to set that the residue equal to 0, and y equal to 2L over 3 is set as equal to 0. When y equal to L, is the residue also set to 0. And because of we assume, okay, in this case we assume this u is a function of cy1, c2, c1y, c2y square, c3y cubed. Then we have the three coefficients, unknown coefficients, c1, c2, c3. So we have to determine this c1, c2, c3, okay, to build that particular function that can represent our approximate our so-called solutions. So in this case, we have three unknowns, c1, c2, c3. So we need a three boundary or three constraint or three equation to solve it. So here it assumes that this residue is forced to 0 at any points. Okay, here is y equal to L over 3, y equals to 2L over 3, and y. So it will give us substitute into that equation. It will give us three equations. So you can solve for C1, C2, and C3. So once we have this C1, C2, and C3, then this equation itself basically is the approximate solutions or equation for our u, y. Okay, so if I want to find the deformations at y equal to 0.5, then we just substitute this into 0.5 into it, then we will find the deformation at y equal to 0. Okay, so that is how it's being approximated. Then if you are looking into the different methods, subdomain methods. So it is assumed that the integral of the error functions over some selected subinterval is forced to be 0. So instead of using the force at the boundary, so basically the integrals in the boundary from 0 to L over 3, L over 3 to 2L, 2L over 3, then 2L over 3 to L. So it basically you have this subdomain of that integral. Okay, integral of this so-called residue function is equal to 0. So just now you are using the residue function. Collocation method is using the residue at different so-called boundary set equal to 0, and we have built the residue at here. Right, this is our residual functions. Okay, that we assume u equal to c1y, c2y squared, c3y cubed. Right. So the collocation method basically set that r equal to 0 at different boundary. So so-called subdomain method, assuming that approximate that our integral of this r or residue function is equal to 0 at different boundary. Then you also will lead you to the three equations. Then it will give you determine the three unknowns, and you build a function that approximate the actual, okay, the deformations. The allocating method required the error to be orthogonal to some weighting functions. Okay, so you come up with a here you come up with another weighting function. Which here is, let's say, phi. Okay. So phi, it could be you have the u, okay. Then you have a phi, basically could be y square, y cube. Then at the end you multiply this so-called this orthogonal so-called this weighting function to the integral of this so-called residue functions. Okay, so at the end you have also three equations to solve for the three unknowns. Then you will get another functions at here. So if you compare later on, this least square is again another method. So you assuming the error to be minimized with respect to the coefficient. So you r square, you minimize this r square. So you have r dr dc basically in this case. So the integral of this again, you differentiate with the coefficients of dc1, c2, and c3. Then it will give you the r dc1, dc2, dc3, the c3. Then it will give you three equations. Then again, you will solve for three unknown. Then this is the function, approximate function that for the deformations. And you compare back to the exact solutions. Then you will see that there is, of course, some differences. Okay, and you can see that the closest will be the least square method in this particular case, right? Compared to followed by, I think, this, okay, subdomain. Then you have Galerkin and you have collocations, right? So again, these are all approximations. So just remember, these are all the numerical approximate. Right? So that is how so-called the problem being formulated. So again, to recap back, in term first we have to formulate the problems before we can solve it using finite element methods. So here we formulate using direct formulation a lot of time, and also the energy method for solid mechanics. So for fluid heat transfer, we use usually we use residual solutions. So we formulate using this, and the most common is the Galerkin methods in a lot of so-called problems, formulation problems. Right. So simple problem like this, exact solution can still be completed easily, solved easily. I mean, the differential equation still can be solved easily. So if the case, in the case of more complex problems, so probably higher degree of freedom problem, then probably we have to use the so-called numerical methods. Here is the finite element methods.